Galileo Galilei was born in 1564 in Pisa, Italy. No, not pizza, stop. He instigated the experimental scientific method and devoted a big part of his life to understanding earthly motion. He once wrote, "Imagine any particle projected along a horizontal plane without friction. Then we know that this particle will move along this same plane with a motion which is uniform and perpetual, provided that the plane has no limits." Does that sound at all familiar to you? Well, it should, because it's merely a rudimentary formulation of what our boy Isaac put forth in his first law of motion. Newton published his laws a few years after Galileo died. Galileo was the first person to truly demonstrate the concept of relative motion, that the motion of an object looks different depending on the frame of reference from which it is viewed. If Jonathan Shetty bounces his ball while standing, he will see the ball take a straight line path wherein it falls to the ground and bounces straight back up. Sunita, who is standing at a distance away, will see the exact same thing. If Jonathan Shetty were to bounce his ball while riding his bicycle, the script would be different. Jonathan would continue to observe the ball move down and bounce back up. For him, the ball is only moving in the y dimension. It is not moving east or westward in the x dimension. However, that is not what Sunita observes. For Sunita, the ball moves from east to west and up and down. The ball takes what we call a downward half parabolic trajectory. The motion of the ball in Sunita's reference frame was different from the motion of the ball in Jonathan's reference frame. The motion observed was different for both. Neither of them was right per se, it was just different. Both reference frames were equally valid. But Galileo was not the sole predecessor of Newton, obsessed with understanding motion. His contemporary, René Descartes, was also intrigued by moving bodies. These people, alongside many others, worked at a time where natural philosophy, or physics, and really science as a whole, was inextricably linked with religion. And so if certain scientific theories were incompatible with religious beliefs, theorists would face backlash from those affiliated with, for example, a local church. Let's say that you joined me here in the void of space, and we're standing about 5 kilometers apart. Suddenly, when you look ahead, you see a gigantic asteroid and a pebble heading your way. You're on a serious collision course, and you cannot escape it. You can either dodge the asteroid and collide with the pebble, or dodge the pebble and collide with the asteroid. I'm watching you contemplate your options. You're smart and know instinctively that the pebble will hurt a lot less than the asteroid. So you do the smart thing and collide with the pebble. Except no. Right before the collision, I pull out a magical remote that turns the pebble into a second asteroid, and you smash right into it. Moments later, I make my getaway and return to Earth in my rocket ship. I'm sorry, your fate just sucked. I suck. R.I.P. Rest in physics. You know, this is sad. The only thing I can think of to make this situation better is to analyze the lethal collision using physics. So let's do it. To better analyze the collision, we have to look at a concept called momentum. Momentum, as is the case with a lot of the physics lexicon, is a word you might have seen being thrown around a lot in everyday life. Welcome back everyone to a special presentation on Liverpool versus Manchester United, brought to you by our new sponsor, the Unreal Junkyard. I'm Jonathan Shetty, and joining me is my co-host Sunita Ghiwala. If you're just joining us, Liverpool are celebrating another goal against Manchester United, giving them a 9-0 lead. They've got all the momentum in the world. Sunita? Yeah, all momentum. Liverpool. What's momentum again? Momentum is colloquially defined as the amount of oomph a moving object has. It is also often thought of as a measure of how unpleasant it would be to get hit by a moving object. And these are all fairly valid interpretations. Momentum is a measurement of mass in motion. Momentum tells you how much mass is moving. The formula for momentum then is momentum equals mass times velocity. E equals mv. Both mass and velocity are directly proportional to momentum. If object A and object B have a mass of 5 and 10 kilograms respectively, and they are both traveling at a speed of 5 meters per second, object B will have a greater momentum as it has greater mass. However, if object A speeds up to 10 meters per second, then they will both have equal momentum. The units of momentum are kilogram meters per second. And momentum is a vector quantity because it's the product of a vector and a scalar, velocity and mass. So why is momentum useful to us? Well, momentum is always conserved, which means that the value of momentum remains constant with time. It doesn't change unless there are external forces at play. If there are no external forces at play, the momentum of a system before an event and the momentum of a system after an event will be the same. The principle that momentum is conserved is called the law of conservation of momentum. Let's apply this law to describe our collision. Well, your collision. The asteroid that hit you weighed 10,000 kilograms. You weighed 100 kilograms. The asteroid was traveling toward you with a speed of 100 meters per second. You were standing still at 0 meters per second. This is all the information we need to calculate your momentum before the impact and the momentum of the asteroid before the impact. The quantities associated with you will be denoted with the subscript y, and the quantities associated with the asteroid will be denoted with the subscript a. If it's the quantities before impact, we will use the subscript I for initial, and if it's the quantities after the impact, we will use the subscript F for final. Your momentum before the impact is your mass, which never changes, times your velocity before the impact, which means it's 0 kilogram meters per second. The asteroid's momentum before the impact is the asteroid's mass, which also never changes, times the asteroid's velocity before the impact. The law of conservation of momentum tells us that your momentum plus the asteroid's momentum before the impact is equal to your momentum plus the asteroid's momentum after the impact. Or mathematically speaking, upon impact, the asteroid smashed into you and the asteroid and you became one object. Both you and the asteroid were traveling in the same direction after the impact as one thing. The momentum of this one thing is equal to your momentum and the asteroid's momentum before the impact. And that value was 1 million, as is seen here. Okay, so we now know that the momentum of this asteroid person thing. But what is its velocity? Well, we know its mass is just the sum of your mass and the asteroid's mass, which is 10,000 plus 100 equals 10,100 kilograms. And then its velocity can be calculated like this. P equals mv, or v equals 99.00990099 meters per second. Do you know what that means? The asteroid was traveling at 100 meters per second before hitting you. And after you squished into it, both you and it were traveling at 99 meters per second. You could barely stop the asteroid. That's how bad it was. The collision was lethal, to say the least. So, that is how the law of conservation of momentum helps us describe collisions in physics. Okay, we played around with this collision using the law of conservation of momentum with the assumption that the law of conservation of momentum is true. But how do we know that the law of conservation of momentum is true in the first place? Well, remember our boy Isaac? Yeah, he's back. His second law of motion, F equals ma, can be rewritten like this. F equals m times delta v by t. This is because acceleration is nothing but how much velocity changes per unit time. We can further rewrite the equation. F equals delta m times v divided by t. And since momentum p is just m times v, we can substitute it into our equation. F equals delta p by t. And we can make change in momentum the subject of interest of our equation here. Newton has helped us realize that the change in momentum of an object is equal to the force applied on it times the time. This quantity is called impulse and is denoted with the letter J. So kind of like how you have change in velocity as acceleration, you have change in momentum is impulse. So what does impulse have to do with the law of conservation of momentum? Well, let's bring in our guy Newton once again. His third law states that, and so that is the key to this conundrum. When this football collides with this marble, The football exerts a force on the marble, and likewise, the marble exerts a force on the football that is equal in magnitude and, of course, opposite in direction. The force that the football exerted on the marble was equal to, let's say, F subscript Fm, and the force the marble exerted in return, let's say, was equal to F subscript Mf. And since these two are opposites, we can say that one is equal to the negative of the other. This is because adding that negative sign to the second force cancels out the fact that they're in the opposite direction. These two forces only came into existence when the two balls were in contact. When they were first moving toward one another, those forces never existed. And then when the balls collided, those forces were induced. The amount of time those balls spent in contact with each other during the collision was equal to 1 second. In that second, those two forces came into play and caused the two balls to bounce backward. The amount of time the marble spent in contact with the football, TMF, was equal to the amount of time that the football spent in contact with the marble, TFM. That is obvious. Therefore, we can say that the impulse or change in momentum of the marble was equal to the impulse of the football, just that they were in opposite directions. The equation for that is Fm times Tfm equals minus Fmf times Tmf. And since we know that F is just mass times acceleration and acceleration is just change in velocity by time, we can say this. If we shift around the variables of the equation, we can see that the impulse is 0. Therefore, no change in momentum on an object means that the momentum is conserved. Anyway, let's return to the asteroid and your corpse. You died a devastating death, and to really get a scale of how brutally the asteroid rammed into you, let us calculate the force of impact. Actually, how about you have a go at it and let me know your thoughts, eh? I'm open to your answers in the comments. Whatever value you've calculated, it's probably quite big, and for that, I'm sorry. I'm sorry for that ordeal you had to endure. I'll fix it. I promise, I'm going to go back in time and fix this. Let's say that you joined me here in the void of space, and we're standing about 5 kilometers apart. Suddenly, when you look ahead, you see a gigantic asteroid and a pebble heading your way. You're on a serious collision course, and you cannot escape it. You can either dodge the asteroid and collide with the pebble, or dodge the pebble and collide with the asteroid. I'm watching you contemplate your options. You're smart and know instinctively that the pebble will hurt a lot less than the asteroid. So you do the smart thing and collide with the pebble. Except no, right before the collision, I pull out a magical remote that turns the pebble into a second asteroid. But instead of ramming into you, it just stops in front of you and starts rotating clockwise like crazy. And you're just utterly confused. But hey, you're safe. The asteroid did not touch you. It won't touch you. And it cannot hurt you. For it has no momentum in any form. Or does it? The asteroid was not at all moving around in space. Rather, it was merely spinning in a fixed position. But it still had momentum. Not linear momentum, which is what we've been looking at, but a different kind of momentum. Angular momentum. What is angular momentum? Angular momentum is a dizzyingly vast concept with implications ranging from the very small to the very large. It's the quantity of rotation of a body, and just like linear momentum, it's conserved when there is no net external force acting on our system. Hi, thank you for watching this video. If you feel certain explanations weren't understandable or you have any questions related to them, please write to me in the comments section or through Gmail. If you'd like to know which resources have been used to research and create this video, I've linked a document containing them underneath. I've also linked a short worksheet that you can solve to test your understanding of this topic. Goodbye.